Authored by a veteran chemistry teacher, Abdul Shakur, these two textbooks provide all the essentials that would not only enable students to master grade 11 chemistry, but to excel at the next higher level in this subject. What make these texts unique are their creativity and profundity with which concepts are explained for clarity and mastery. The following is one of a set of 44 different tutorials created by the author, using materials primarily from the text Chemistry 11 in Focus. I hope you enjoyed this video. If you liked it, please give it a thumbs up and don't forget to subscribe. We will see you in the next video and thank you for watching.
Our lesson today deals with Gay-Lussac's law and the combined gas law. We first of all discuss Gay-Lussac's law, or what is sometimes called the pressure and temperature law, and then we show you how the gas equations for Boyle's law, Charles's law, and Gay-Lussac's law can be combined to give the combined gas law equation. But before we discuss Gay-Lussac's law, we need to have a quick review of the investigation of Jacques Charles on gases. We'll just quickly go through that so we can compare that with what we'll be doing today. In Charles's investigation of the effect of temperature changes on the volume of fixed mass of gas at constant pressure, the plunger of the syringe was free to move back and forth to negate any pressure changes of the gas within the syringe. If you can recall that when Charles investigated the effect of temperature on the volume of a fixed mass of gas at constant pressure, the gas within a syringe was heated, but the plunger was movable. So any increase in pressure within the syringe was negated by the outward movement of the plunger. So the pressure inside stayed constant. Unlike what we were having now in the formulation of Gay-Lussac's law, here you're having a fixed mass of gas that is kept at constant volume. In other words, the volume of the gas is not allowed to change. That happens by keeping this plunger here in a fixed position. To see the effect now of temperature changes on pressure of the gas within this syringe here, this gas here is subjected to higher and higher temperatures. And for each temperature change, the new pressure inside here is recorded. So recall again that as the temperature of a gas increases, its molecules will be gaining kinetic energy and they'll be bombarding against the walls of a container more forcefully, and therefore one will expect an increase in pressure within the syringe here. Why? Because now this is immobile, it can't move, so it cannot move outwards there to negate any pressure changes. This is what they did. In experiments to determine the relationship between pressure and temperature changes, the temperature of the gas in the syringe is gradually raised and its new pressure is noted and recorded for each new temperature change. So you see this table here now, what it shows? This table shows the different temperatures to which the gas in the syringe was subjected to, all right? So you started with the temperature at 25 degrees Celsius, 35 degrees Celsius, and then you change it to eventually 60 degrees Celsius. Now at 25 degrees Celsius, the measured pressure was 100 kilopascals. We call that P1, and we call that temperature the T1. Note how we have to add 273 to change temperature from Celsius to Kelvin, because these relationships will only work well when the temperature is changed from Celsius to Kelvin. So in every case, we added 273, and these are the temperatures there with the corresponding pressure. So at temperature 298 Kelvin, the pressure there was 100 kilopascal. When you raise the temperature to 308 Kelvin, you can see there was an increase of pressure here. We call that T2 and we call that P2. Raising it further to 333 Kelvin, you'll see here there was an increase of pressure. Okay? Now what Gay-Lussac found was this, that in every experiment that was done, is that 3 experiments were done, if you took the pressure and you divide it by the Kelvin temperature, it turns out to be a constant. If you divide that pressure by that temperature here, you get a value here. If you divide the second pressure by the second temperature, so you can see what is happening here, you're getting a constant. So this is the equation, the law equation that was established by Gay-Lussac, that the pressure over its Kelvin temperature gives you a constant. All right? So you can express that in a different way now. You can say, since all these results are the same, you can say that P1 over T1 is equal to P2 over T2 and can also be equal to P3 over P3, depending on how many experiments you've done there. So generally, this is another way of expressing the pressure-temperature law, or the Gay-Lussac law. Let's see if you have a problem there, or we can solve a problem using that. So look at it. The walls of a sealed gas cylinder can only withstand 1,000 kilopascal of pressure. We've spoken about that already, in the necessity of knowing what pressure gas cylinders can withstand before you can fill it with a certain amount of gas. That is the maximum pressure it can withstand. If the gas in the cylinder had that pressure, to what temperature must the cylinder be heated before its safety valve opens to prevent an explosion of the cylinder? What does that mean? Let us say, for some reason, this cylinder here that had a gas had that pressure and that initial temperature, right? If you, by accident, place this cylinder where temperature is very, very high, okay, you can cause the cylinder to burst, unless it has a safety valve that is open at a very high temperature to release the gas inside. So you want to know at what temperature it will reach that pressure there, okay? See what you're given. You're given P1, you're given T1, and you're given the final pressure there. That is the highest pressure you can withstand before the valve opens, okay? Hopefully the valve is working well. If the valve doesn't work well, and you heat it up too much beyond that, then it will explode. Establish the equation here, and you're looking to what? You're looking for T2, okay? So this is what you're going to do. You take T2 across there, so it becomes T2, P1, and then you take that across there. I'll show you how to do the math, and you take that across there. So what you're going to have, your T2 is going to be up here, and your P2 T1 is going to be there, and you bring down your P2 there, okay? All right. Did I do it right? You're looking for T2. So you take that there. This should go off, and this should be a P1 here, okay? This should be a P1 there, all right? There should be a P1 there. Okay. So you insert those values there, and you find that you get that Kelvin. Then you want to subtract 273 from that to get what temperature. So at 919 degrees Celsius, that's when the valve will open. So that's the maximum temperature. You can heat that up. Any temperature below that, you'll be safe for that cylinder of gas. And here are some questions that are based on Gay-Lussac's law. You're given 3 entities there. You're asked to find the fourth, okay? Now you have the combined gas law. All right, let's see how they arrive at the combined gas law. Now let's look at Boyle's law. Volume is inversely proportional to pressure. So here P1 and that is P2. You can see that P2 is greater than P1. And you can see in this case, the temperature and the mass of the gas are fixed, right? So PV is a constant. So that's the first equation there. Charles's law, in this case, you have a temperature here, and then you have a temperature T2. In this case, T2 is greater than T1, and the pressure of the fixed mass of gas is kept constant. And because of that, you get a rise in volume. So in this case, V is directly proportional to T, and we say that V over T is the constant. So that's second gas law. Third gas law. In this case, you're keeping the volume constant and the mass of a gas. You never change the mass of a gas in any of these cases. So P2 is greater than P1, all right? As a result of that, we say that there was an increase of pressure inside here because you're changing the pressure of the gas there, right? And this we're saying here is that this is a constant that you get here, okay? Let's combine all of these together and see what happens. So this is Boyle's law equation. This is Charles's law equation. And this is the one for pressure and temperature law. You can see in every case, temperature is the bottom there. Temperature is the bottom. In every case, V and P are the top there, never the bottom. So when you do that, you combine that, all of these laws, get what is called a combined gas law here. A PV over T is equal to a constant. What this helps you to do, it helps you to calculate one entity if you're given 5. So if you use this equation here, you can say P1 V1 over T1 must be equal to P2 V2 over T2, right? If you're given 5 entities, you can find the 6th one there, okay? If you're dealing with Boyle's law, you can remove temperature there because the temperature stays constant. So what you'll end up with here, you'll end up with Boyle's law here. Okay, that is if temperature doesn't change. There's no change in temperature, so you remove that and you end up with Boyle's law. Now what about Charles' law? What do you remove? Pressure doesn't change, the pressure doesn't change, so you quote the equation again, take out P. So this is how you derive Charles' law. V1 over T1 equals V2 over T2. Now if you want to know what Gay-Lussac's law or pressure and temperature law, what doesn't change? Volume doesn't change. And this is what it is. So you can derive all 3 of these laws from the combined gas law equation, okay? So let's look at that question and see how you can apply that combined gas law. A syringe has that volume. You can make the V1, okay? And this is at that temperature T1, okay? And you have a pressure of that. It's placed in a refrigerator at that. So what will be the final pressure? If the plunger is fixed, so you're talking about Gay-Lussac's law there, okay? All right, so use that one there. You have 3 things, and you want to find the final pressure. You put in a refrigerator, obviously it's going to get cold, and the pressure is going to be most likely less than that. Let's see. You know V1, okay, you know V2 is the same. You know P1, you know T2, and you know T1, all right? So well, you need what? You need P2? You need P2. So V1 and V2 are the same, okay? So you have this equation here, you derive the pressure law equation there, all right? You're given the volume, they don't change. So you get P1, T1, and T2. So you need to find P2. So you leave P2 there, take that T2 up, take that across there, okay? So P2 will be equal to P1, T2 over T1. Put in those values there, and again, that is going to be the pressure, new pressure, and it told you it's going to be less than 100. So you put in a refrigerator there, where the gas molecules are having less kinetic energy. What's this one now? Now you're given some stuff here. You have a balloon that's filled with a helium balloon with that volume and at this temperature, okay? And you get the initial pressure. So you have 3 things right here now. Volume, temperature, and pressure. And it is lower to where the temperature now is, 20 degrees Celsius, okay? So it's high up in the atmosphere, it's coming down now, it's coming closer to the earth, right? And the temperature now is higher there, okay? And the pressure, of course, is higher. So it's up there, there's a balloon up there, high in the atmosphere. So this is the earth here. We've spoken about that already, all right? A balloon is small, 4 liters up here, all right? When you bring it down here, 2 things will happen. The temperature is going to go up from negative there, it's cold up there. It goes up to 20 degrees here. And of course, the pressure on the balloon also increases as you go down, right? So you have initial volume, initial temperature, initial pressure, the final temperature, final pressure. You want to know what new volume it is going to have. So you're going to use the combined gas equation, and you let V2 be the subject of the equation. All right, given those things there. So now you make V2 the subject of the equation. You want to know what is the final volume. So keep V2 here, keep that there. Look what you're going to do now. Take T2 upstairs here, all right? And bring down T2 down there, okay? I'm teaching you guys a little bit of math there so you know to do that. So you will left all, you'll be isolating V2. So V2 will be equal to P1 V1 times this T2 you took there. And it'll be over T1 times this P2 that you're bringing them there. Now you put in those values there. You put in all those values. That's P1. That's your V1 there. That's your T2 there. Okay, that's T1. And that's your P2. And your V2 is 1.73 liters. See, it's shrunk from 4 liters to this because it's experiencing a higher atmospheric pressure there. Okay, never mind, you have a little bit more increase in temperature. The change in pressure was more drastic than the change in the increase in temperature. So then you have some questions there for you to do based on the combined gas equations, okay?